Okay guys, so we're starting section 1.4 and it's about continuity in one-sided limits. So the first thing that we want to talk about is something that is continuous. Okay, something that is continuous. And something's continuous if you can draw it without lifting the pencil off the paper. Okay, that is continuous. Why? Because I can draw that without lifting the pencil off the paper. And let's say I had something like this. Let's say I had this point here and it went to here. And this was 1, 2. And let's say that this one was, I don't know, 8, 5. Okay? There will be a y. There will be a y for every x value between 1 and 8. There is a y value. Okay? There will be a y value for every x between 1 and 8. Okay? And that's part of what being continuous is. So this next part is important. It's important that you write this down. You can have it in your notes. You could see this on a quiz or a test, so you might have to reproduce it. It's a good way of testing whether or not you guys have good notes. So the definition of continuity at a point. So there's 3 kind of things that we look at. Number 1, f of c. So we're looking at some point c. So at a point we'll say c. F of c is defined. There has to be a y. That point. Number 2, the limit as x approaches c of f of x exists. Okay? And what does that mean? Well, as x gets close to c from the left and the right, the limit exists. And then number 3, the limit as x approaches c of f of x equals f of c. Okay? So if I want to draw a picture of this, so there's your number line, okay? And you have this function, okay? And let's say that this point right here, the coordinates for that point are c and f of c. So like that's your x and that's your y. Okay? That's c. Okay? So that is the definition of continuity at a point. Okay? It has to pass those 3 conditions. And if it passes those 3 conditions, then we can say that it's continuous. Now, the function might not be continuous forever. It could be continuous over a closed interval. Okay? But that's what it means to be continuous at a point. Make sure you have that in your notes. Okay? I would say that's pretty important. So let's say we had this one. And they want to know, why isn't this continuous? Why isn't this continuous? Okay? So we're going to say that this is a number line, and we're going to say that this is some point c, and we're going to go through our conditions, and we're going to see if they work. Okay? We're going to see why this isn't continuous. What's the reason this is not continuous? Well, let's take a look. Number 1, f of c is defined. there has to be a y for that point. Well, let's look. Here I am at C. Is there a point anywhere there? No. So it fails the first condition. Okay? Why isn't this continuous? F of C is not defined. Okay? So there's our first example to look at something and say why it's not continuous. Let's look at another example. We have something that's very similar. So now we're looking at this fictional point C again. And we want to see whether or not these conditions, we can pass through these conditions. F of C is defined. Well, I do have a value right here. So is F of C defined? Yes. So no problems here. Number two, the limit exists. As I come from this side and come from this side, does the graph converge on the same y value? Yes. So we have no problems here. Let's look at the third condition. The limit of f of x has to be equal to f of c. Well, the limit of this is let's say that's 4. I don't know. Let's say that the y value there is 4, when this value is 2. These two are the same. It doesn't pass this. Why isn't this continuous? Because the limit at f of x as x approaches c is not equal to f of c. Here is f of c, and here's the limit, and they're not the same. Okay? So that is our beginning look at continuity, okay, and whether or not something is continuous. So we've got a little bit more notes, and then we will jump in and do some problems. Okay, so a list of continuous limits. Okay, list of continuous limits. One polynomial. Okay, continuous at every point in their domain. Okay, let me put that up here. Continuous at every point in their domain. Number 2, rational. When you have something like p of x over q of x, okay, but where q of x doesn't equal 0. You got a 0 on the bottom, it's not going to be continuous, okay? But, so wherever q of x is not 0. 3, radical. Okay, so like, I don't know, the nth root of x, the square root of x, the cube root of x, something like that. And then we have some of our trig functions. Okay, so these are different types, lists of continuous limits. Now, again, this is kind of important. It's continuous at every point in the domain. Okay, so if the domain is restricting values, then it's probably not going to be continuous there. So there are 3 types. This is big. 3 types of discontinuous. 3 types. Number 1, we have a hole. And we've already looked at some of these that are a hole. Okay, it goes like this, there's an open circle, and it looks like this. That's an example of a hole. 2, we have what's called a gap. Okay, and a gap is an asymptote. And then 3, we have what's called a jump, and that's like an absolute value where you have something like this. Okay, the asymptote looks maybe, I don't know. Okay, so those are your 3 types. Of those 3 types, this is the only one that is removable. Okay, removable. And these 2 are both non-removable. Okay, now they call it removable because we can fill the hole with a piecewise function. Okay, so why is it removable? Removable. Because we can make it continuous with a piecewise function. Okay, fill the hole. So, why is it removable? It's removable because we can fill it with a piecewise function. Okay? So, we're going to look at some examples. How can we tell what's what? How can we tell if something's an asymptote? How can we tell if it's a jump? How can we tell if it's a hole? Well, hopefully you've thought about it a little bit, and some of the things we talked about in the course, and we talked about in statistics as well, so that you guys are in there. How can we tell? Number one, graphic. Okay? Graphic. Always great to graph functions to get a feel for what it looks like. Okay? So I'm going to take this down so that I can put it up. Let's see what we got, guys. Let's see what we got here. So we're going to graph. We're going to do some graphing. All right? Put my overhead on. Let's put on Ladybug. Let's do some graphing. So let's say I had this function here. Let's say I had f of x is equal to x squared plus 2x over x cubed minus 1. And there, our domain is x cannot be 1. So I want to see what's happening here. Okay, so I go to my graph, I go to my graphic calculator. I don't expect you to do any of these by hand. I do not, okay? I expect that you're going to do these with your graphic calculator. So I clear out what's in my y equals screen, and I'm going to have a parentheses here. I don't know if you guys can see that or not. I'm hoping you can. I'm typing in parentheses x squared, and then I've got to go down. Oh, okay, x squared. I like this one. It's an old calculator. Minus 1 end parenthesis. Looks like I got too many parentheses there. Let's do that again. Parentheses x squared minus, I'm sorry, I'm doing the wrong one, plus 2x squared plus 2x, all right? And then I'm dividing that by x cubed minus 1, okay? I can hit graph. Well, what does that look like, guys? What does that look like? I don't know if you can see that or not. If not, type it in your calculator. Now you really can't see it. You'll look at the viewfinder and see if that's something you guys can see or not. Kind of. You can kind of see that. It looks like an asymptote. Okay, it looks like an asymptote, which I'm going to call a gap. Okay, so I think it's going to be a gap. I think so. And so I go over here, and I'm going to write down what I think it is. I think it's a gap. But, you know, I want to be sure. I want to be sure. I want to see what's happening when x equals 1. I know that's going to cause a problem in my denominator. That's where my problem's going to hit, right? If you look at your graphic, you can kind of see that. X equals 1. There's problems there. So I've got to take, what I want to do is I want to see what's happening as we get close to 1. So I could hit a table if I wanted to do a table. Second table. I should do this first, second window to do table set. Tables start at 1, delta, point, 0, 1, and then I'm going to go to my table, and I look at what happens. Look at what's happening as we get close to 1. What's happening as we get close to 1? I've got some crazy values there. Again, I hope that you are doing this on your graphing calculator, because you might not be able to see this. Doing the best, very best that I can. So if you can see this, it says at 0.99 it's negative 99.66, and then at 1.01 it jumps all the way to 100. That's telling me that we have an asymptote there, which is why I wrote down a gap. Okay? So what's one way you can tell what type of discontinuity you have? Graph it. Okay? Graph. I think I have another one. I do. Let's erase this one. And let's write this one down. So let's say I had x squared minus 1 over x cubed minus 1. And again, they're going to tell you that x can't be 1. So we're going to want to tell and investigate what's happening as we get close to 1. Okay, so let's go to our graphing calculator, and let's clear that out. Let's type this one in. So I'm going to have x squared minus 1, okay, on the top, divided by, on the bottom, x cubed minus 1. And I go to my graph. It doesn't look like I have an asymptote there. Okay, it doesn't look like it. It looks like I've got a little inchworm. It goes up and it goes up, it goes straight and it goes up and it goes kind of straight again. So let's look and see what happens. You could zoom. I mean, I'm not good at zooming. Not good at that necessarily. But look, it looks like it's continuous, doesn't it? But we know that it's not. We know it's not continuous because we know that if we plugged in 1 here, it would make a 0 in my denominator. But when I look at my graph, it looks to be continuous. So let's investigate what's happening as we get close to 1 again. Okay? So I think my chart is still probably in there, my table. So I'm going to go to my table and let's look. Let's look at what happens here. So I'm trying to fight the shadows here. Okay? It says, if you can see this, it says from 0.97 it goes 0.6767, 0.673, 0.67001, and then on the other side of 1, 0.66334, 0.66. Well, this looks like it's going to be a hole. They're converging on the same y value. It looks like the limit here would be equal to, say, something like 0.67. So I would say that this one is a hole. Okay, this one is a hole. We can tell why. We tested it numerically by looking at a table. Okay? All right. We are moving, guys. We are moving. So let's look at some more. And investigate. Okay, let's investigate what happened in here. Let's say I had this. F of x equals, I'm not even going to put a numerator. I'm just going to put a denominator. And I'm going to ask you, do we have any discontinuities with this function? Could I have any discontinuities with the function? Okay? And I would say no, because no matter what, I can never make this denominator 0. I can plug in anything I want for x squared. Because I'm adding 1, I can never make my denominator 0. No discontinuities. So if you have even powers in numbers, no discontinuities in the denominator as long as that's plus. If it's minus, then we can do it. Okay? Let's say I had this. F of x equals x plus 3 over x minus 2. Okay? This one here is going to be a gap. This is going to be a gap. Gap at x equals 2. Okay? So there is a little hint when we're dealing with fractions.